Everybody. Today it's a real pleasure to have Chris Chen from Caltech. So Chris is a first-year grad student at Caltech. He's working with Garnet Chan and John Preskill. The talk he's giving is based on work he did at UC Irvine as an undergrad, where he was working with Steve White, and he was also working with Miles Stoudenmire from the Flatiron Institute at the Simons Foundation. And Miles is going to join us as a panelist after the talk. So, Chris, looking forward to your talk.
Okay, thanks, Umesh, for the kind introduction. Right, so hi, everyone. So today I will be talking about this work called the Quantum Fourier Transform has in small entanglement, which is in collaboration with Miles Stoudenmire from Flatiron Institute and Steve White from UC Irvine. So I'll start with a brief overview of our work. So the Quantum Fourier Transform is one of the most important ingredients in quantum algorithms. However, we'll show that the core part of the QFT can only generate small entanglement on qubits, and I will explain soon about what core part and small entanglement means. We can then simulate the QFT classically using tensor networks, which can be faster than fast Fourier transform in many practical cases. But this is not a bad news for quantum computers, because it doesn't mean the QFT can be simulated classically for arbitrary inputs. For example, stating Shor's algorithm will have an expensive tensor network, which I will also explain a little bit later. So here is a brief outline. So I will start with some introduction to the Quantum Fourier Transform and the related concepts. So the Quantum Fourier Transform has been widely used in quantum algorithms for provable speedup over their classical counterparts. And as I said, the most famous example is the Shor's algorithm for factoring integers, and there are a lot of other applications of fault-tolerant quantum computers. So the Quantum Fourier Transform's power stems from its ability to find periodic structures of quantum state, which many quantum algorithms rely on to gain a provable speedup. So when we talk about Quantum Fourier Transform, we usually mean over the cyclic group z up to the power of n, which is essentially the discrete Fourier transform over Hilbert space spanned by n qubits. So in terms of matrix, we can say this is exactly the discrete Fourier transform matrix, where this omega here is the phase depending on the number of qubits. And in this bracket notation, its Q is a bit string formed by n qubits. So the quantum circuit of the Fourier transform can be decomposed into two parts, which I call a core part and the bit reversal part. So the core part is essentially consists of Hartmark transform gates and phase gates. And this dot here basically means a controlled gate, where if the first qubit is 0, you apply the gates on the rest of qubits. Sorry, you don't apply the gates. And if the third qubit is 1, you apply all these gates on the rest of qubits. And the second part is the bit reversal, which is essentially swiping the order of the bits. So it can consist of a series of swap gates between the first, the last, and the second to last, and so on. So from now on, we'll actually refer Qi as the QFT and Fn as the DFT, which means that I will only care about this sort of the core part and drop the bit reversal, and I will call this part as Quantum Fourier Transform. So the entire circuit I will refer as the discrete Fourier Transform matrix. Then I will talk about the main results. I will start with some informal statements, and then I'll gradually build up the formal statement of our paper. So informally speaking, our paper especially showing that the Schmidt coefficients of the QFT and the DFT actually differ significantly. And I will define soon about what I mean by Schmidt coefficients. So it turns out Qn has an exponentially decaying Schmidt coefficient for any partition of the operator, suggesting small entanglement. This is our work. And the Fn, where we include the bit reversal, actually has a uniform Schmidt coefficient for any partition of the system. And this is done previously by in these two papers, which suggests maximal entanglement. So that is most entanglement in the full Fourier transform operator comes from the bit reversal. It's not the part where you have the recursive structure. So why do we consider Schmidt coefficients? So there are actually many variants of operators entanglement measure, but we specifically consider operator Schmidt decomposition because they lower bound the non-local communications required to implement the operator. It also indicates representability as an efficient tensor network, in particular matrix product operator. They often capture the maximal entanglement the operator can generate by bipartite mixed quantum states. So it's not like the definition that is maximal entanglement, but often it's very close to those. And for the bit reversal operator, we can see that it's a very non-local operation because it swaps all qubit pairs between two subsystems and can generate large entanglement on a subsystem of your quantum states. So to be more formally, we define the operator Schmidt decomposition of a unitary matrix acting on a bipartite system, A and B, as the decomposition of this form. So where chi, this number here, is the Schmidt rank, and the sigma k here are the Schmidt coefficients. And this operator A and B acting on two subsystems will satisfy some orthogonal property in the space of the operators. And this big N here is essentially the Frobenius norm. Sorry, square root of N will be the Frobenius norm of the unitary matrix, and because it's a unitary, it's essentially the product of the dimension of two subsystems. And because we choose that we have this extra factor here, the Schmidt coefficients are actually normalized. So usually when we do this decomposition, the coefficient get are not normalized, but because of this constant here, there's nice property that they're normalized, and we also order them from the largest to the smallest. So this is actually equivalent as the singular value decomposition, just like the Schmidt decomposition of a quantum state. So we first reshape the unitary into a matrix in the vertical direction. So for example, for this unitary here, we bend the two wires on the top to the same direction and the wires at the bottom to the same direction, which forms a matrix in the vertical direction. And then we apply the singular value decomposition to this matrix in the vertical direction, which we broke into three parts. And then this is essentially a sum of our product of two operators acting on two subsystems. And the orthogonal property of these operators A and B I mentioned is essentially due to when we do a singular value decomposition, we get isometry matrices on the for this A and B answer. So just to have an example, the operator Schmidt decomposition of a swap gate is essentially the sum of polys. So as we can see, it has a maximal Schmidt rank, which is 4 for 2 qubit gates. And it also has uniform Schmidt coefficient, which suggests it has actually maximal Schmidt stress or like operator entanglement, loosely speaking. And this explains why the bit reversal operator has a very high operator entanglement, because it consists of a lot of pairs of swap gates. So for our main theorem of the paper, to state it more formally, we're basically considering the Schmidt decomposition of the operator Qn, and we choose a partition of our operator where we the first subsystem A will be consist of qubits 1 to j, and since the other subsystem B will consist with qubits j plus 1 to n. And it turns out the Qn has the Schmidt decomposition of this form. And for the Schmidt coefficients, we find that for k greater than or equal to 2, it has this extremely fast exponential decay. And it turns out this decay is actually independent of the number of qubits and partition of system, because there's no dependence on n and j in this decay relation. So even if you have infinite number of qubits, for any partition of the operator, you still have you can still see this exponential decay. And just a side note here, we notice that the Schmidt rank of QFT is actually still exponentially large. So you will so it's just that the Schmidt coefficient decay very quick, very fast. Okay, that was actually talk about, before I go into details of how I prove this and some other related stuff, I will talk about some implications of these results. So just a rough picture of what I just said. So what I was basically saying is that the QFT has a high Schmidt rank, but somewhat limited correlation length. And you actually only require a few bipartite communications to accurately approximate the operator. So basically means if you partition the operator into two parts, most communications between two parts are somewhat truncatable. So does this result pose any complexity hierarchy issues? Sadly or happily, no, because classical simulability requires both operators and states to have a small entanglement. So for example, Shor's algorithm actually has exponentially expansive state before QFT. So there's no non-classical representation of the states. So even without knowing our results, which is QFT's low entanglement, some of early work already showed that approximate QFT is efficiently simulable if input circuit has limited interaction range and log depths, or log bubble width, which is a term used for the graph of tensor networks. And semi-classical QFT is also efficiently simulable. So if the input state is already cheap, we actually don't need to know anything about QFT's low entanglement for it to be simulable. So essentially, our result doesn't add too much in terms of computational complexity. So does this result tell anything new on implementing the QFT on quantum computers? So for this, I actually don't have a definite answer, but I think some expert in the audience might have a better view on this. But for me personally, I think generally it means that low entanglement implies fewer resources needed, and it's also more robust to noise. However, some qubit architectures may not favor input-output to have a different ordering. So it really depends on what kind of platform you're implementing the Quantum Fourier Transform. It's also not clear whether it implies a lower circuit depth, because any QFT with approximation error below 1 or 10 actually requires at least log n depth. So it's very hard to reduce the depth of the circuit based on the how much you approximate a QFT. And there's this low entanglement also implies that there might be an underlying exponentially decaying Hamiltonian for the quantum Fourier transform, but it's kind of hard to find this Hamiltonian, and I will explain this in details in later sections. So does it tell anything new on the classical Fourier transform? This answer, it turns out to be yes, because for the low entanglement nature, with the low entanglement nature, simulating the QFT can actually gain speed up over fast Fourier transform in many classical algorithms. So for example, if input is certain types of tensor networks, we almost always favor simulating QFT on it over doing just naive fast Fourier transform. So if input is a vector, we can still gain advantage if it is compressible into certain tensor network. So we can convert into some efficient tensor network first, and then we can simulate QFT over it, and then we can still get some speed up. And I will explain with more details in the later section. Okay, so then I will dive into some of the methods I use to rigorously prove the decay of the Schmidt coefficient and some intuitive explanations of this result. So the underlying mathematical reason for the exponential decay of the QFT Schmidt coefficient can be understood through 3 steps. So firstly, it turns out this recursive circuit of Qn has a generalized recursive circuit, from which we can actually see that only phase gates are relevant to Schmidt coefficients. And from the phase gates, we find that the Schmidt coefficients of Qn are actually equivalent to singular values of the top left submatrix of the DFT matrix, so which I refer as Fn. So the submatrix of DFT matrix are actually known to be approximately low rank. So they are extensively studied in signal processing as the spectral concentration problem. So this is actually something you can just search online, and there's a wiki page about this problem. So what is so let's talk about the first step. So what is a generalized recursive QFD structure, QFD circuits? So usually when we construct the recursive part of the QFD operator, we usually think about, so we first construct the QFD for n-1 qubits, and we apply a bunch of controlled phase gate on it, and then we apply 8 hardware gates on it. So this is the usual way to construct the circuit. However, it turns out it can be generalized into where the H gates can be expanded into like higher dimension quantum Fourier transform. So essentially, so this H gate will borrow one phase gate from here and an H gate from this part and form a 2-qubit QFT. And this central part will borrow some control phase gate to this part, which forms some more complicated structure here. And then this part will become a smaller quantum Fourier transform. So here I choose to show a 4-qubit example, and I choose j equals to 2, but you can imagine this works for any number of qubits at any partition. So you'll always have this form. And for this central part, the phase gate are in the central part only if and only if it goes across the partition of your system. So it depends on the choice of j. So because the two smaller QFT circuits are locally unitary with respect to the partition, so we can say that only the central part where the phase gate that goes across the partition is relevant to the Schmidt coefficients. So we only need to focus on this part to tackle the Schmidt coefficients. So let's take a look at the structure of the central part. So it is an operator that's diagonal in a computational basis because all of these are control phase gates. And its matrix elements are actually product of phases conditioned on the bit value of the two registers, so the upper register and the lower register. So notice that I actually labeled two registers in the opposite direction. So this will be useful later. But you can see that it basically introduces a phase that depends on the bit value of it's like a complete relationship between the bit values here of the two registers. So if we do some analysis, we can see that all this phase can be just combined into a very elegant equation where it only depends on the decimal value of the register. So there's no ratio of a single bit string. So we just combine all bit string into a single decimal number. And it's just this single phase here. And just to remind, we want to show this phase is actually related to the DFT submatrix later in step 2. So just to summarize what I did for step 1, basically I'm saying that for quantum Fourier transform, you can always decompose into 3 parts. So there are 2 parts as a smaller QFD circuits, which is irrelevant to our analysis. And there's a central part, which is a diagonal operator that has diagonal elements that's somewhat related to the elements of discrete Fourier transform. And I call this part sigma nj. And it turns out the Schmidt coefficient of Qn and cut j is the same of Schmidt coefficient of omega nj. Let's now take a look at step 2, which is how this is related to the submatrix of discrete Fourier transform. So the non-zero Schmidt coefficients of omega nj are actually equivalent to the singular values of submatrix of the DFT. Because if we do some calculation, we can see that we can sort of when we calculate the Schmidt coefficients, it's basically doing the singular values of the reshaped matrix of this operator. So we combine these two into a single cat, and these two into a single bra. And then because these are duplicate dimensions, we can actually drop the dependence of this, and then we have this nice operator here. And this operator is exactly just 2 to the power of j times 2 to the power of n minus j submatrix of the discrete Fourier transform matrix. Because instead of summing from 0 to 2 to the power of n minus 1, here we have 2 to the power of j, and here we have 2 to the power of n minus j. So the submatrix. So let's now go to the step 3, which is why we know this has to be a low rank matrix. So the submatrix of the DFT are known to be approximately low rank because it relates to the spectral concentration problem, which has been extensively studied in signal processing. So the original problem actually considers discrete time Fourier transform, but in our case we use discrete Fourier transform. But nonetheless, it still have the same spirit. So the spectral concentration problem basically wants to find a strictly localized sequence in this window here, whose discrete time Fourier transform is maximally localized with a finite window here is a 2W relative to the frequency periodic window. So it's this larger window here. So the solution of this sequence are known as discrete spheroidal sequences. So the idea is basically that, because this is a finite window in the time domain, when we do discrete time Fourier transform, we have this periodic structure. And we want to only focus on this periodic window. And we want to select a smaller window here, which I calculate the sort of the power within this range, and want to vary the input to see. You can think that when I vary the input, the signal will also change drastically, and the power in this range will change. And I want to just keep varying the input until we find that there's a sequence that gives the maximum power within this range. So we can actually, so in our case, because we're using discrete Fourier transform, is actually sort of a discretized problem of this original spectral concentration problem. So instead of constraining to a strictly localized time sequence, we constrain to be localized right to a periodic window. So this actually can be viewed as discretizing in the frequency domain. So it will have this larger box, and we just copy this larger box a few more times, and here you can already see why this is related to the submatrix of discrete Fourier transform, because the discrete Fourier transform maps these larger blocks into this larger block. But here we only focus on this smaller block and this smaller block in the time and frequency domain. So with some analysis, we can show that essentially it's a maximization problem, and actually this can be directly mapped to an eigenvalue problem or singular values of the DFT's top left submatrix. So what's the property of the submatrix of the discrete Fourier transform? So for an R times C, so R refers to the number of rows and C times refers to the number of coulombs, submatrix of n by n discrete Fourier transform, the singular values actually have a clustering behavior. So essentially, you have a sort of like pseudo degenerate region where you have a R times C divided by n number of eigenvalues that's very close to 1. And after that, you see like an extremely fast exponential decay here. So remember, for our quantum Fourier transform, we always have this 2 to the power of j times 2 to the power of n minus j submatrix. So which means that only one singular value is actually close to 1. And it's also independent of the choice of j and n, because when we time this number of rows and number of coulombs together, we got 2 to the power of n. And if we divide by 2 to the power of n, we got 1. So it's basically for any j and n, we only have one single value is close to 1. So we see this exponential decay immediately. So that's sort of the reason that in our bond, there's no dependence on j and n at all. So to prove this rigorously, we can use some techniques that people in signal processing has developed, which employs the decay property of half-order Bessel functions. And all these interesting details shall refer to our paper to see how this is derived. Okay, just to summarize, so the Schmidt coefficients of the QFT are singular values of DFT submatrix, and DFT submatrix is related to the spectral concentration problem. So spectral concentration has a decaying solutions corresponding to the QFT's decaying Schmidt coefficients, and the upper bounds are independent of the number of qubits and the partition of the system. So let's now talk about something more intuitive about the QFT's load entanglement, which is some relation to the area law. So it's still not intuitive why the QFT circuit with the long-range gates and non-constant depths can have a small entanglement. So can we interpret the QFT as a physical process, which is evolution under some Hamiltonian with constant time, and understand the low entanglement from there? So there are a huge amount of literature that's studying this type of topic, but there's a result that's saying that there's error law for dynamics. But for 1D, you can just interpret as for a Hamiltonian 1D lattice, if the interaction range decaying faster than 1 r squared, then the Hamiltonian always has constant entangling rate. So in other words, when evolving an arbitrary 1D system with such Hamiltonian, the rate of the change of the system's entanglement entropy actually does not increase with the system size. So it seems that QFT fall into this category. So is this really true? So it turns out explicitly solving the QFT's Hamiltonian is a very challenging task because hard mark gates and control phase gates do not commute with each other. However, recall that from our previous analysis that Schmidt coefficients are actually only dependent on the phase gates. So therefore, if we remove all the hard mark gates, the Schmidt coefficients will actually be invariant for any cut. So in fact, we can show even more, which is that any bipartite entanglement measure under the local operation classical communication principle will remain invariant from removing the hard mark gates. So this is actually very nice because this Hamiltonian is this operation is a diagonal operator, and it's very easy to derive the underlying Hamiltonian for this operator. So it turns out this Hamiltonian is exactly an exponential decay interaction. So even though we do not explicitly solve the Hamiltonian for QFT, we can find a Hamiltonian that have the same entanglement structure with the QFT's underlying Hamiltonian. So this means that QFT must have sort of a similar behavior, but it's just that the operators might be too complicated to find. Okay, and lastly, I will talk about some work on doing the simulations of the quantum Fourier transform. So the quantum Fourier transform small entanglement implies that it has an efficient tensor network representation. So in particular, matrix product operator representation. So to find it, we will first consider decomposing the controlled phase gate into some low-rank local tensors. So I wouldn't talk in details, but essentially you can think this control phase gate as a copy tensor and two phase tensors. And this copy tensor basically takes all three inputs. Only evaluates one when three inputs are the same, and this phase gate only it gives a phase when this top index and the horizontal index have the both one, and this three other phase tensors are give a phase only when the x1 and x2 are both one. So this actually allows us to decompose the entire QFT circuit into a pretty compact tensor network, which we call the QFT tensor network. So to efficiently construct the QFT MPO, we can just view this entire tensor network as a series of matrix product operators, and we can apply any MPO and MPO multiplication algorithm with bound dimension capital constant to construct the matrix product operator. So we use the so-called zip-up algorithm because it's both fast and stable in our case due to some nice property of the these phase gates. So assume we set the bound dimension of the QFT MPO to chi. The construction algorithm will generally have a time complexity that scales with the third power to the bound dimension and the square to and squared to the number of qubits. And the time complex and the constant associated with this complexity is also very small. So for example, for 50 qubits, it only usually take around 1 second to construct the entire MPO. And the total truncation error will scale linearly with the number of qubits because we're doing truncation for all cuts of the operator. And its scale its scale especially small with the bond dimension. So for fixed error is that for fixed this number, the bond dimension will grow logarithmically. So this is some remarks on the error. So in the column, this number of qubits will increase from 6 to 8, and in the row, this is the number of qubits, and in the column, this is the bond dimension, which will increase from 2 to 8, and we sort of calculate this quantity to represent our error. So you can see that if we set bond dimension to 8, you can. This is actually already less than machine precision. So you can see there's already fluctuation here because for n equals to 8, we actually observe a smaller error compared to the previous one. So essentially, we can treat it for practical purposes. We can treat this as exact, or we can say that the bond dimension can be sort of treated as constant because it grows so slowly. So our QFT MPO is actually efficient enough to be classically practical. So which we sort of call the super classical Fourier transform. So what I mean by that is that, so for example, if the input is a matrix product state with a bond dimension chi-m, applying the QFT MPO on this MPS will have a linear complexity. So it scales linear with number of qubits, the bond dimension of the MPO, and the bond dimension of the MPS. So if the input is a vector of a length and n to the power of a big N to the power of 2 to the power of small n, we can convert it to MPS first using, for example, randomized SBD, which takes about exponential with the number of qubits, but linear with the bond dimension of the underlying MPS. So compared to FFT with type linear with number of qubits, we still have that advantage if the bond dimension is sublinear. So for example, for constant bond dimension MPS, we will always gain some advantage over by just doing this naive simulation. So we can even be faster by using more efficient conversion methods such as so-called tensor chain cross interpolation. So just to mention a few, so here I only think about the time of converting MPS to, a vector to MPS because it actually dominates the time of applying, both constructing the QFT and applying QFT on the MPS. So we actually only need to consider this part. So here are some benchmarks run on the personal classical computer. So for compressible data, we can already see that advantage at around 18 qubits. So this black line, so this green line is the fast Fourier transform. So as we can say, it's independent of the structure of the input because it's just a matrix multiplication. So it scales around especially with the number of qubits because it's a log scale. And here, for the black line is this is some randomly generated data, and we both compare that we start with a vector and convert into a MPS and apply Quantum Fourier Transform MPO on it, and as well as we start with MPS already and just apply the QFT MPO on it. So as we can see, if it's a random data, we don't have an advantage at all because we expect the MPS to have an exponentially large bond dimension. However, for some more structured functions, such with some periodic structure, so even with some cusps, which is not where the first derivative is non-continuous, we can already see that there's some advantage even when we're including the time of converting it to MPS first. And if we start with MPS already, that is solid lines, we can see that it has a sort of exponential advantage compared to fast Fourier transform. So this actually implies many classical applications because operations with fast Fourier transform become very cheap in matrix product states. So we can apply it to quantum chemistry, quantum dynamics, differential equations, and so on. So this is what I'm currently working on. So for example, the Fourier interpolation, convolution, Laplacian, which can be diagonalized by Fourier transform, and also split operator evolution in some quantum dynamics problems. So there's also evidence that the bitwise encoding of functions through matrix power states and matrix power operator is actually very powerful. And Fourier transform is actually an addition to this family. So we can actually combine all of them to do fast classical computations. So some examples including, so many functions actually have an explicit efficient construction as a small rank matrix product states. So for example, cosine, sine exponential, finite order polynomials can be directly converted into matrix product states where we can write out the elements of each tensor individually. And this usually self-similar functions also have this behavior of having small bond dimension when converted into MPS. So there's also evidence that probably all Lipschitz continuous functions have a small bond dimension, where loosely speaking, this just means that the derivative is bounded by some sort of constant. For bitwise operations and finite state machines, we can also directly convert them into efficient MPOs. For example, some addition, just a ripple carry adder, for example, and also some shifting operations. We can directly write out the elements for each local tensors in the MPO. So just a side note, this was something I didn't realize when I was writing the paper, but a natural question to ask is whether the same low rank structure applies to the approximate QFT, which is something people have been studying a lot in the quantum computing community, which is defined by removing the long range controlled phase gates. So for example, for the approximation, so with zero approximation, I always have the full circuit. For approximation level with 1, you remove the longest, the control phase gates with the longest interaction range, and the approximation 2, you remove this further. So numerical simulations actually suggest that matrix product operators for this approximate QFT actually have a higher bound dimension, which is actually quite counterintuitive. And this was sort of previously found in this paper by Jielun. And the low rank structure seems to be a feature of the QFT's full circuits. I don't have a rigorous argument for this yet, but I just think this is something that is interesting to know. Okay, and then I will end with some future outlooks. So first thing I'm curious about is that whether these results really imply a better implementation of the QFT on quantum computer. So for example, there is some related work where we can convert the matrix product states into a quantum circuits. So can we do the same for the matrix product operator by sort of, for example, minimizing a unitary with the minimize the distance between a unitary with the QFT MPO. And for analog quantum computers, we can also try to see if we can time evolving an exponentially decaying Hamiltonian with constant time to construct the QFT operator. So the second question is just what I just said is that approximate quantum Fourier transform. Why does approximate quantum Fourier transform seem to have a higher entanglement than the full circuit quantum Fourier transform? And can we generalize this result to more general groups? Can we also find more classical applications of results? And can we even categorize a general class of classical problems where we can employ the structure of this QFT MPO and to achieve some speed up or fast Fourier transform? And lastly, we can ask whether we can connect this QFT MPO to other faster Fourier transform. So for example, the previous post-film is the sparse Fourier transform, which says that if your frequency domain is only have a few spikes, you can sort of achieve exponential speed up in some cases. So is there any relation between all these different types of faster Fourier transform? With that, I will end with some acknowledgements. So thanks for Miles, Stoudenmire, Steve White for the amazing collaboration. And thanks for Sandeep Sharma, Garner Chen, and Chen Group for the insightful discussions on the classical applications of the results. Thank you for the attention.
Okay, wonderful. Thanks for a really nice talk. It was very stimulating. I guess in a certain sense, you could almost say, well, if you leave aside the open questions about how to speed up the quantum Fourier transform quantumly, this is almost like one aspect of your results is it's a quantum inspired classical algorithm.
Yeah. Yeah, exactly.
And then there's something else that occurred to me, which maybe we can discuss further in the panel, which is, obviously you think of the bit reversal as being, I mean, if you just think about it, it's not entangling the state very much, but as an operator it is. So, exactly where it stands with respect to the role that entanglement plays in quantum computation, maybe we can tease it out a little further about, maybe we have to think about the right definitions, or what we think of there. But
yeah.
In the meantime, let's see if there are any other questions before we move to the panel. Oh, Frank, I guess you can just speak up, and you can also speak on the panel, I guess. But
actually, I have a question about the talk, really. So two questions actually. First, about the approximate quantum Fourier transform. So the way I have always looked at this is that this is already a matrix product operator approximation of the quantum Fourier transform. So in which the bond dimension is basically the number the exponential of the number of digits that you keep. So how much worse is that? Because then you don't even have to compress anything. You immediately have a matrix product operator approximation of the quantum Fourier transform up to a certain precision. So how much worse is that one than your compression?
Right. So I think that depends on how much approximation level you make. So if you make the approximation level like relatively large, I guess you can see that converting that directly to MPO, you have a pretty small bond dimension MPO, I guess. But if you, for example, you only have approximation level 1, if you increase the because the approximation level here I use is just removing gates instead of the number of computer physics gates I use. So for example, if you have a larger system, you only remove one large gate, and you still expect this increasing in the bond dimension, I guess.
Yeah, but you have to. It's at the end. It's about the scaling, no? And if you look at the scaling, you only say, okay, I want to approximate things up to machine precision. That also means that you don't that you only keep a few kind of the qubits. So the approximation level is not the right kind of measure to look at. So you just say, okay, I only keep the qubits that act on a range, let's say, of 5 or 10 qubits or something. And that gives you immediately an MPO of bond dimension 2 to the 10.
Yes, exactly. So that's actually sort of in the range of, so it's like about here. So you can see at here. So for example, if you keep up to 5, it's sort of like this point. You can see it's still sort of constant. I guess this sort of reflects that a little bit, even though it's not directly related to that, to like converting that to that PO. Does it make sense?
Oh, yeah, not complete. But actually, I have a second question, if I may. So, what about the fermionic Fourier transform? Because then you actually have to add some kind of swap gates. Does that change anything in your analysis?
Yeah, I believe that changed a lot. So there was a previous work on like spectral tensor network on this fermionic Fourier transform. But if you look at it, what it does is actually a much more complicated operation than just quantum Fourier transform, because it contains like both 1 particle, 2 particle, 3 particle cases, and mixing it into a large operation. And there's also a lot of non-local swap gates. So in that case, like even we drop the fermionic swap gates, it doesn't have a low rank structure at all.
So, and then I'm confused about the application in quantum chemistry, because for this you need the fermionic Fourier transform.
Ah, I see. So, by that, right. So in quantum, so by that it's more like what we do. For example, if we want to do Hartree-Fock calculation, there's for example the Coulomb operator. We can use that to sort of like we can use fast Fourier transform. We can approximate a convolution with this fast Fourier transform using this convolution theorem, for example. So that's what I sort of mean by application to quantum chemistry. It's not like applying fermionic Fourier transform in quantum chemistry. Yeah.
Okay, great. So Stefanos, do you want to wait till we are on the panel, or we can just do the questions from the Q&A and then move to the panel? Would that be okay?
Sure.
Okay. Okay. So so Chris, there's a question on the
okay.
Sorry, and if you can stop sharing, there's a question on the Q&A. You can see it. Thanks for the very nice and clear talk. Can you comment on your classical QFT MPO method, how it compares to the QTT FT method by Dolgov?
So for their results, they are basically saying that if you give MPS, I can just directly simulate the QFT by applying the circuit layer by layer on the MPS. So it's like if we go back to let's see, if we look at the right, so these slides here. So what they are saying is that instead of converting this entire thing as a single MPO, I apply this MPO first on my one state, and then this MPO on my state, and then this MPO on my states. So the problem with their framework is that you cannot really guarantee what's the entanglement weighting between applying these MPOs. So by showing the entire QFT has a small entanglement, we can sort of have a guarantee on that how much entanglement the entire thing can be generated. And it's also relatively more efficient because there's no fluctuation of entanglement when applying this QFT between this MPO. So it's like we can compress the entire operator first and apply it directly on the states.
Great.
Yeah.
Okay, thanks. So let's see. Yeah, Chris, if you can stop sharing your slides, then
sure.
To the panel. Okay, so let me start introducing the panelists. Frank Verstraete, you already heard from a little bit. Frank just moved, I think, from Ghent University to University of Cambridge. He's done really fundamental work in the entanglement of quantum many-body systems, including defining PEPs, which are beautiful model. We have Miles Stoudenmire, who is he's one of the co-authors of the paper. He's at the Flatiron Institute at the Salmons Foundation. So he's done this incredible work on using tensor networks to to model sort of chemically accurate effects, temperature effects, and he's also responsible for this iTensor software. And we have Stefanos Kourtis from the University of Sherbrooke. So he was a co-author on this recent paper, which on tensor network contraction, which gave sort of 5 to 6 orders of magnitude speed up. That was used in the Google the spoofing classical algorithms for the Google supremacy experiment and all the follow-up experiments. So really great to have you all here. Maybe let me start with your reactions to the paper, and maybe also Stefano, you had a question, so maybe you can wrap it all into your comment.
Sure. Yeah. So thanks, Chris, for the awesome talk. I really like this paper. I saw Miles a couple of weeks ago at a workshop in New York, and I conveyed my enthusiasm to him as well. I have one specific question regarding the spectrum of the DFT. So the spectrum of the DFT looked flat. Most of it was flat, except for an exponentially decaying part. And I'm wondering whether, even though you have volume law entanglement, the fact that the spectrum is flat tells you that there might be some simplification that is not evident. Because, for example, if you look at stabilized or Clifford circuits, you get flat entanglement that can be volume law, and yet you have efficient classical simulation algorithms when you have this entanglement structure. Could you comment on this? Could there be some underlying structure one can exploit even to decompose the DFT in a certain way?
I see. That's a very interesting question. I guess when I mean flat is sort of referred to the sum matrix of DFT, and it's like so in the case of QFT, it's a little bit subtle because you don't actually have that flat region because you say that it decays immediately. But if you have a different partition of the Fourier transform material, we see that flat region. But I actually don't really know if this is really related to if there's any way to sort of employ this to sort of like flat to sort of go across this flat region. Because I think I don't see a direct connection between like this DFT for sum matrix with what you said about like Clifford circuit or so, because it's it's a little bit I think I just say I don't know the answer to this question.
I would tack on that I agree with your point, Stefanos, like that if you just made for example, if you take a state, if you just make a random MPS, random state, and then you try to decompose it and look at a Schmidt spectrum, it will generically decay, I mean, as you know. So then you would think, flat would mean something like more special is going on. Like there is structure, you would think.
Exactly. So, I mean, if you take a random vector and try to SVD it, then you will get a Marchenko-Pastur, right? So yes, you will get like a power law decay. You will get an exponential number of non-zero Schmidt values, but they are distributed a certain way, and they decay algebraically. And this is the decay that we saw, or like the behavior that we saw in that spectrum is very different. It's like a flat for a certain time and then just decays exponentially. So I was thinking maybe that this is interesting. Something tells us that there's something interesting, some simplification could be possible that is beyond just the typical SVD or matrix product structure. And in fact, I was wondering if one could like generalize your approach in this work and say, well, let's look at any classical algorithm, write it in terms of an operator acting on bits, and then look at the spectrum. So basically, it could be like quantum inspired anything, right? So you look at any algorithm, you write it as an operator, try to decompose and see if the singular value spectrum reveals some simplification that you missed.
So can I comment actually on this? So the fact that you have symmetries, that you have degeneracies in the Schmidt spectrum is actually always a consequence of symmetries. And of course, in the quantum Fourier transform, it's really like this is the transformation you have to do to diagonalize or to find the E-reps of your group. And of course, it's like it is very much tied to symmetries, and that's why if you would do this for indeed this more general question, if you don't do the quantum Fourier transform for U1 but for a general group, these Schur Weil transforms, you will get something very, very similar. You will always get these kind of huge degeneracies of Schmidt eigenvalues, and this is actually all a consequence of the symmetries in your in your system. And actually this is something that is typically, if you do matrix product state calculations, this is always something very interesting. If you see degeneracies in your spectrum, it means that maybe you have something like topological order in your phase, or this witnesses something interesting going on in your state. I'm not sure that this makes things clearer to you, but indeed degeneracies are typically go hand in hand with symmetries. So it's not a coincidence that these degeneracies are there.
Yeah, I would just say that this interesting property of this have a Flatiron and decay prop, and then like another Flatiron of zero single value is like people are still trying to sort of understand this the reason of this. I think like in signal processing, and because this spectral concentration problem is actually sort of a very fundamental problem, and there's actually no like analytical solution of this eigenvalue world. So I think it's still sort of like people are still trying to find a like more general argument why this thing has happened, and I think it will probably lead to some interesting answers to some of the questions. Yeah.
So could I ask also something unrelated? I would like to get this out of the way, right? Because I don't know if we have any number theorists in the room, but and you also commented briefly on Shor's algorithm, but I wanted to like follow up just to make absolutely sure. So, so in the case of semi-prime factoring, okay, where you need to run the full Shor's algorithm to get an answer, could there be like some subset of semi-primes for which entanglement could be low, running the full Shor's algorithm that we didn't identify before, like a subcategory of semi-prime factoring for which we can have an answer more efficiently, say, than the best field sieve classical methods for factoring?
Chris, do you want to take that?
So I don't know too much about that, but like the entanglement in Shor's algorithm is like usually we'll see that in the bound dimension is actually proportional to the period you actually try to find. So it's like but I think it's like this is sort of like a generic behavior. So I guess it's probably like it's only dependent on the period you try to find. So I'm not sure if that's sort of like you can have a a sneaky way to go across this. It's probably not very possible. Yeah.
Okay, thanks. I suspected as much, but I just wanted to have a absolutely clear answer on that. Thanks.
So can I ask another question?
Sure.
So something that is very interesting and where Fourier transforms are used all the time in physics simulations is for things like Gross-Pitaevsky equations. Okay, you have to kind of evolve non-linear differential equations, and it includes Laplacians and things like that. And well, this is very annoying to implement, to discretize and so further. But things like Laplacians are very easy to implement in the Fourier world. So is this something? Have you looked at applications like this? Because this would be the first thing I would try to do. Like, does this lead to can I solve something like the Gross-Pitaevsky in a much more efficient way using your method? Because that's the kind of that's the kind of dynamics. This is what you do. Now you go to momentum space, implement your derivatives, then go back to real space, implement your kind of potential, and react with your potential on it. Have you tried this, or is this the kind of things you want to do? Or
yeah, so even for example, some simple simulation like time dynamics of a particle, you have this Laplacian operator, and you can, if you quantize, you represent everything as MPS, you can have this, you can use the KFT MPO to map into the diagonal, in the Fourier space, and then you can have a, which is basically a x squared function in the Fourier space, and then you can map back, and you can have this low rank structure. But actually, even without KFT, there's in this actually MPO encoding of Laplacian using finite different methods is already known to be low rank. So it's just a tridiagonal. For example, if you use order 3 finite different method, you have this tridiagonal matrix, which you can actually directly construct the MPO representation of that. So I think it's more about the whole story of like having what's the framework of like converting everything to this MPO and do calculation within this this framework. So it has I think people have been exploring using this to do higher order differential equations and so on. It's like it's a relatively active research.
And it can immediately imply some nice results too. Like Chris listed some functions that are known to have very low bond dimension, like an exponential or a sine or a cosine in real space. But then immediately this result about the Fourier transform MPO means that if it's low bond dimension in K-space, like smooth or has some simple structure in K-space, then it's also low bond dimension in real space. It just provides a very tight link between those two spaces as well automatically.
Yeah. Yeah, for example, an interesting example is that circular matrix can be diagonalized by Fourier transform. So if your circular matrix have some nice property in the for their eigenvalues, you can actually simulate the circular matrix in this MPO setting relatively easy.
Can I ask a follow-up question on that? Sorry. Yeah. So, which is there's something that is a little bit being debated in the quantum computing community when you use quantum computer to solve classical or quantum differential equations involving unbounded differential operators, right? So one thing that the quantum computer has the power is to resolve a huge number of grid points with a logarithmic number of qubits. But of course, when you if the smoothness of the underlying function is bounded by some constant, you kind of expect that at the end of the day, I mean, you will pretty much going to resolve it either quantumly or classically. So does your result or a generalization of this kind of thing imply there is a better way to design classical algorithms to match this superpower by quantum computers as well?
Yeah, I think it doesn't directly imply that, but it somewhat suggests this can be a good route to like do some classical. Because so in principle, you can basically map any non-deterministic finite state machine with sort of like constant number of transitions to this MPO setting, but you have the power of compression, so it's like you don't have to go to the full rank space. You can throw away small singular values. That's something you can employ to sort of do this. For example, for the smooth functions, even though they might have full rank, you can still have like throw away most of the singular values. So I think yeah. So I wouldn't say it's like it's like directly implying that, but I guess it suggests that we can try to see what's the power of doing computation with this framework.
So to be more concretely, I mean, there's something I don't know how to think about this problem. Let's say if we do dynamics, and as you evolve your dynamics, the function can often become more and more non-smooth, right? Which means that the bond dimension should presumably increase. So on the quantum computer, the cost should pretty much be the same. On the classical computer, the cost may become higher and higher. So is there, do you think this difference will always be there, or there is some sort of way to make the classical simulation more efficient to even bridge this gap?
I see.
I think certainly something analogous can be done on the classical side to what's being done in the kind of, if you want, second quantized framework, where we have MPS for 1D, but then you use PEPs for 2D, and it might, be further, or like use a Mira or things like that. I think so far this technology has mostly just been explored at like the MPS level, but there's certainly potential to try other tensor networks that can capture more entanglement. That's one. Another relevant thing to your point, I don't know if you've seen this work by Goryanov et al. And it's like Dieter Yaksh and some others, where they simulated the Navier-Stokes equations using this exact same framework for representing functions and for representing differential operators and things like that. And what's really interesting is they find that indeed, it's just like you said, it's very smooth velocity field at the beginning. Then it gets more and more turbulent, and there's more vortices and things developing, and the entanglement grows, but it's still actually very modest. And they find that it actually really closely corresponds to the Reynolds number. So they find that the higher the Reynolds number, the more entanglement you need, Also, they find a difference between 3D fluids and 2D fluids. So there's all kinds of interesting hints there at like more of a theory, maybe roughly analogous to how we have like area law for quantum systems, and it's sort of like a something like that, but for classical functions embedded into quantum states as tensor networks.
Interesting. So this is still the QTT type of study, right? As in the previous Q&A question.
That's right. But I think there's a lot more to do than has already been done. I mean, I think we're in the very early days of that now.
I see. Thank you very much. This is very helpful.
Right. So Umesh had a power outage. The weather in Berkeley is quite crazy right now. So I'm just stepping in to moderate.
I can confirm that.
Yeah, so I think he's running to his office. He might be online soon, but I'm happy to moderate meanwhile. There's maybe one question on, okay, the Q&A question has already been answered. So any other questions, comments by the panel?
So what about 2D Fourier transforms? Is this something that has like an efficient people description or something? Did you look at this?
Right. So for 2D Fourier transform, it's just a tensor product of two 1D Fourier transform. So for example, if you think about, you can think about you encoding your function into a 2 by n perhaps, and it has degree of freedom n squared. So it can represent a 2D function, and you can just apply two tensor product MPO on each row of the PEPs to sort of simulate 2D Fourier transform.
But that means that you would generate lots of entanglement with this. You would get an area law of entanglement, basically.
Just a quick comment there. It's like you don't really need a PEPs though here to represent the 2D function, right? You could just use like an MPS with doubled site dimensions. So you just have an X index and a Y index on each MPS tensor. If by 2D, Frank, you meant like a function of two variables, if that's the 2D that you meant.
Yeah, it's difficult to understand, but I figured that they would get something like instead of an MPO, you would get something like a PEPO, but maybe that's not. Maybe this is naive. So you say that this is not.
Usually if you think for 2D function, I think it's not from MPS to PEPs. It's more like you have a few it's, for example, for 2D you have two times of the number of sites for your MPS, and 3D is 3 times the number of sites because the grid point grows especially with the number of sites you have. So for example, you can encode your MPS. For example, you can just link to MPS to represent your MPS 2D function, or you can think of some clever interlacing, between the site points. For example, the first site represents encodes the function in 1D, the points in 1D, and the second point side sort of encodes something in 2D, and third side is like interlacing or like other type of arrangement that might lead to lower entanglement in some cases.
But anyway, I think the reason that there is this whole talk is to see what is now really quantum to this quantum Fourier transform, because it seems that more and more things that we all believed that was quantum is actually not really quantum. No, that these tensor networks are kind of doing lots of things. So you have kind of a complete fresh perspective on all these questions, I think, as a starting PhD student. So what is your feeling? So what is where will quantum computers be useful for? What are the kind of, what is the really quantum kind of part now of, let's say, Shor's algorithm? Where is this hidden now? Because everybody was always saying, well, this is the quantum Fourier transform, but that's obviously not true.
Right. So I think for quantum computers, it has the power to sort of just ignore the entanglement and doesn't care about it. Well, classical is like for lots of problems sort of unavoidable. But there are a lot of cases where you can see that, for example, in this case, you can see there's some underlying symmetric structure or whatever. It's like allows you to have employing the low rank structure, but it wouldn't like. I think this class is like people are still trying to define what are really these functions or what are really these operators are. And I think it would be really interesting to generally answer these questions. But I think it's just that people are discover more and more operators that actually have an underlying structure that doesn't generate this huge entanglement somehow. You know?
I mean, I really like that question because to me, it says something roughly like that, exactly as Chris said, you need the quantum computer when you expect to have high entanglement. But now we see, at least if you're in this function representation use of your qubits, it's like high entanglement might mean something like a function which is highly not smooth, like maybe something which is a sum of delta functions, and the delta functions are at like totally random locations in your continuum. Maybe something like that. Like that's the kind of thing that you just simply cannot represent classically this way efficiently. But then even functions that have like a fractal structure, which Chris mentioned on a slide, those can be actually low bond dimension. Like quite a few things can be really low bond dimension in this representation, low entanglement.
Sorry, I missed a part of the discussion. We had a power outage in our neighborhood, but back on campus. So I wonder whether you discussed some of this, but there were two things that occurred to me. One is, of course, to what extent do these tensor network methods to what extent do they really speed up classical algorithms more generally? But then there's a second thing, which is this looking at the low entanglement piece for a classical function. So to what extent is this happening in deep learning, or where you're looking at this corner of function space? So have you thought about these sorts of connections?
I think it's a good connection to make because there's already some really nice work by some of the same people actually who invented this technology, this tensor train framework. Some of the same people tried putting, basically it's like the analog of a 2D function in this representation as the weight layer of a neural network, a priori, like putting it in before they knew the right weights, then training, doing backprop through the weights in that, always staying in that form. And they found that they could reach close to state-of-the-art performance of the neural net while having a huge compression of the number of parameters they needed. I don't think it's widely used in the machine learning field, but it's a really nice idea, and it seems to work.
And do you think it, in addition to being an idea that works, do you think it has explanatory value, in terms of?
I think so, at least in that case, because there's a whole toolbox then to analyze those functions efficiently. You have this huge weight layer, but you have it compressed. So you could, with this QFT MPO that Chris came up with, you could do a spectral analysis, for example, but many other kinds of, the whole entire applied math toolbox can be recast in this compressed form, it turns out. Like Chris mentioned, differential operators, like so many things. So you can kind of bring that whole toolbox onto it. But what's nice about it, say in that case, would be, I guess, in sort of very rudimentary kind of deep learning, like if you didn't have any sort of convolutional structure imposed, if it was just an arbitrary weight layer, I think there's a general freedom for the weights to sort of connect up any way they want, however the dynamics of the gradient descent would want. But if you pre-imposed this kind of compressed form, you would have pre-imposed an ordering to those, qubits now, which are like the weights. And so I think that would at least give you more of a hope of interpretability, because you kind of demanded this ordering so that you stay in this low rank space the whole time. So at least you kind of could reconstruct things a little better without having to like do a bunch of swaps afterward to sort of figure out what the weight layer was. Maybe there's already other ways to find a better ordering. I'm not an expert on that.
Yeah. So what I would find very interesting is to see whether there's some underlying principle of like what functions can you efficiently represent with matrix product states, in the sense that these are functions that are like eigenvectors of something like local, something that is local. Okay, this is exactly the whole point of matrix product states, of course, in quantum Hamiltonians, is that if your quantum Hamiltonian has a local structure and the ground state is basically a matrix product state, and there should be some underlying, very similar property for for all the functions that you can represent efficiently using these matrix product states. And what is very nice, of course, is what this work shows, is that you have this function can be represented, and also the Fourier transform of that function has an efficient representation, and all the kind of things that you do has like indeed it's all consistent. But I think something like that is completely lacking. We don't understand at all what is the what is the underlying principle of the functions. You say, okay, maybe all Lipschitz, I forgot, you said this in your talk, I think, no, Chris, that all Lipschitz continuous functions.
Right.
But is there a notion that all? Yeah, I think there's a notion that all these functions have actually very few Fourier coefficients or something that is known, but there should be more than that.
Yeah, I do think this is a very timely question, as we briefly discussed earlier. I remember about 10 years ago, heard Kourtis and from Max Planck and talking about this thing, which is using this QTT format to compress the Hartree-Fock calculation to do enormously large, dense grids. Now it seems like a little bit ahead of his time, but indeed a lot of the foundational things have been built there. And given that recently there is this Google collaboration paper talking about the simulation of exact quantum dynamics, compare that with the classical mean field methods, but the speed up is really come from this almost exponential increase in the number of basis functions. And so whether you can do that do something that is better from a classical perspective by understanding the entanglement of this classical part of the basis functions. That seems to be a very, very interesting question.
By the way, I think that's totally right on the money. I mean, Kourtis was really way ahead on a lot of this stuff, so highly recommend his work. But one nice thing too, when you mentioned chemistry, it made me think that a really nice kind of basis set to use is just a grid, because it's like automatically orthogonal and has a lot of nice properties. But often, grids don't scale too well. And what's kind of nice about this approach is that you are implicitly using a grid representation, but then you're compressing it. So you get like a lot of the advantages of using a grid, but you sort of don't have as many of the disadvantages of using it in like a naive way. So that's one kind of potentially exciting thing about this way of representing functions too.
That's right. Yeah, I mean, with a grid, you have a lot of other good properties as well, especially when we go to interacting chemistry and with this diagonal representation. Yeah, those are definitely very, very useful techniques.
So Umesh, I also wanted to go back to your question about the swap kind of circuit, why this is so entangling. So this is, of course, well known. This is like the kind of quantum information questions that people looked at more than 20 years ago. Is like what are the most entangling gates? And indeed, the most entangling gate that you can have is a swap operation. Although a swap on itself will not generate entanglement if you apply it to a product state. Because if you have two like maximally entangled states and you swap these two qubits, then you generate immediately two times, like, yeah, you generate like two bits of entanglement. And this is indeed somehow the reason that this swapping of your gates is indeed so hugely entangling. There's nothing, there's really, it's only interesting if you swap things that are already entangled with other things. And in that sense, it's indeed completely useless entanglement if you're not entangled with something else. So by the way, this was also like the big problem. This whole idea that swapping is actually can generate lots of entanglement was a big problem in trying to formulate like the question how much entanglement can be created under time evolution, like under quasi-adiabatic time evolution. I think Chris also briefly talked about this, and you talked about this in your talk. Now you suggested that indeed the fact that your quantum Fourier transform does not generate lots of entanglement because there is indeed like a Hamiltonian with exponentially decaying terms that cannot generate lots of entanglement because of this way how much entanglement can you create with such swaps and all this, and there's now a complete kind of picture of how this works. But this was very the difficulty in proving all this is exactly to get rid of the swap type of arguments.
That's great. It's kind of like an entanglement distillation argument almost, because you can have maximal entanglement if you spread bell pairs across a cut. You will get the maximum entanglement, but that's trivial, right? And so this is why when I see a flat spectrum, I'm wondering, is there a way to distill just belt pairs and just throw them out of the computation? And just to only do the relevant part.
Yeah, if I might comment on this, this is exactly what happens actually with tensor network algorithms where you exploit symmetries. This is exactly, you don't, like if you have something like an SU2 symmetry, Miles knows this very well. You have like an SU2 symmetry, you basically don't care about you only care about your 6J symbols, let's say, about your representations, your labels of representations, not about your magnetic quantum numbers. Okay, these because the entanglement that is generated by these quantum numbers is the one that give rise to your flat spectrum, and these are not interesting. So you can have a huge speed up in simulations by indeed taking advantage of the fact that you know that there's lots of flat pieces, that you have lots of degeneracies, and this is exactly what is being done when you simulate, when you use symmetries in tensor network algorithms. But what is even more, things like the toric code. Okay, if you look at this, this also has like a very flat spectrum. Well, this is like a Hamiltonian that is, well, it has an area law of entanglement, but effectively, if you look at it in some way, this is just a product state. It's a product state in a basis of gauge functions. Okay, so you can really kind of see this as a product state if you impose the right symmetry to your wave function. And I think this is exactly the direction that you want to go to. Now that indeed, like something like the toric code is actually has zero entanglement if you look at it from the point of view of symmetric tensor networks.
Yeah, but I think it must be beyond what we call symmetries in physics, right? Like the typical symmetries, because you can write stabilizer states without any symmetry, right? Any physical space symmetry. And it's in fact the non-stabilizerness, or like sometimes people unfortunately call it quantum magic, that actually generates non-triviality. And so yeah. That's,
no, I completely agree. It's just that if you have something like some translation variance or so, for these cases, it's understood. I think this is at least an indication that what you say is indeed it can be realized. Yeah.
If I can go back to the quantum-inspired side, meaning the classical simulation of this, now that you are unconstrained by unitarity and all other things imposed by the quantumness, are there any other speed ups you can imagine in the classical simulation of the QFT that would allow you to do things even faster? And here I'm thinking maybe something like amortized, gaining some amortization speed ups. Like if you want to Fourier transform many functions at the same time, could this be somehow exploited? Like you sometimes in deep nets when you have convolutional layers and so on. You mentioned convolution at the end of the talk also as a potential target. Do you have any thoughts on this? How to go further?
Right. I think actually I feel like this is just the very first step of understanding this low entanglement structure of QFT, because there's actually still a lot of interesting part of the QFT that we weren't really able to solve. Like for example, like when we increase the number of qubits, you actually see all the local tensors approach to themselves. So they have sort of like a self-similar structure within the tensors. So I think in order to sort of answer your question, I guess I personally feel it has to be like understanding like what's really going on to like be like underlying for this low entanglement structure of the QFT. So yeah. So it also really connects to like a lot of other algorithms that, as mentioned, like the sparse Fourier transform, where because if you have just a few Fourier coefficients, you will also think that the Fourier transform of if you only have a few Fourier coefficient, you also have an efficient matrix problem state repetition of that. So maybe there's some inner connection between all these kind of different algorithms we're employing the structure of the Fourier transform that to gain this speed up. So
Yeah, Chris, I had a related question for you. I mean, we've talked about this a little bit, but I know you've been thinking about it. You mentioned in your talk a bit. So this is, a kind of compressed quantum-inspired linear algebra. But as you know, there's other proposals in the quantum literature for like linear algebra. I mean, there's famously, this HHL algorithm, but then there's a lot of newer ones. There's this whole QSVT and everything. And so do you have a sense if this is kind of like hinting more about other strategies to dequantize certain cases of those that's different from the previous approaches that have been pioneered, and whether it's giving insights about whether certain special cases of those might be more simulable than thought using tensor networks, say, as the framework?
Right. So I think the techniques I use in this paper is like very specific to quantum Fourier transform, because I have to employ the low rank structure of the submatrix of DFT. But you can sort of like, for example, for quantum single value transform, it has a very interesting structure of these repeating blocks. You can actually sort of model it as some kind of matrix products and tree tensor network structure, and you can sort of see some low rank structure from it too. Like if you have some assumption on how the single value like distributes within this block encoded operators. But yeah, I think it's like it's so related to the previous discussion that it's not very clear like what when will these functions are like compressible into MPS and or like tensor network in general. So
are you meaning some of this might have to be empirical too for a while, like just try
yeah, I personally feel
the way you tried, where you just put the layers on an MPS or MPO and just see that kind of thing too a little bit?
Right.
Yeah, just to add quickly on this, I think the success of QSVT, which just uses one Scylla qubit, shows that the power of this quantum linear algebra algorithm is not on that particular single qubit, but on the block encoding. So if certain block encodings of some sparse matrices or some other things can be dequantized efficiently, I think this is something that is what the literature hasn't really explored too much. Previously, the dequantizations mostly dequantize this matrix polynomial structure. The result is like for certain problems, the polynomial order is low, and therefore you can dequantize it in a black box way. But can you go into the details of this block encoding and ask whether that block encoding can be dequantized? I think that's could be an interesting thing to know.
Actually, I have a personal question to ask you, Chris. So did you think at some moment that you had, because of this, that you had an efficient algorithm for factoring? And if so, what did you do?
Okay. Right. So actually, we sort of discovered this while simulating Shor algorithm. So in Shor, we're just trying to see like what happens for the entanglement in Shor algorithm. And when I construct this operator for quantum Fourier transform, I saw, oh, it has a low entanglement. So I just decided to investigate why that's the case. But after that, I immediately think, does it imply like Shor algorithm is really simulable or not? But after thinking about it, so it's like so you actually really need both input state and the operator to be efficient. So in Shor algorithm, it's like the input state to the QFT is actually very expensive. It's like the entanglements of the order of the period you try to find. And for large numbers, you usually expect very high one dimension. So it's like yeah, so it's just like it doesn't really so just after thinking about that, I just dropped the idea of simulating Shor algorithm.
Yeah, but it could well be that all the entanglement is because of swap gates, no?
Oh no, I meant the state that before the QFT. So it's like it's not the like.
I think that's what Frank means. Like what if that is just some accident of how Shor wrote?
Oh, I see.
And if he had just put it in a different order arbitrarily, what if what if it's a hidden structure? Or,
Right. Yeah, that could be. That's an interesting thought, but so the Shor algorithm before Shor algorithm is like doing this having this function map all the universal prediction of all bit strings. And usually for that function this is like it's like sort of I feel it's sort of generically have this high entanglement structure. So it's not really about this swap gates, but yeah, but I think yeah, it's probably something worth exploring as well.
Yeah. That's one comment I just wanted to make. I mean, when Chris was talking about the genesis of the project, that was something that was a bit unsurprising for me in the end about the whole project, was because it was really that he and Steve White were just trying to simulate Shor's algorithm just to see what would happen, like at what part in the simulation would their computer catch on fire? Was it, the first part or the second part or what, And then Chris really honed in on this QFT and kept finding that it was very compressible. But what was really interesting to me in the end personally was that it really started out in this mode of like simulating, right? Where the idea is that the classical computer is just trying to imitate this very powerful quantum computer, and we're just seeing like how far it can sort of keep up with the quantum computer. But by the end of the project, I had almost the reverse feeling in the end, that like almost like what the gift that quantum computing might be giving us, we thought was a program to run on some futuristic hardware. But what if it's just a program that we run today? Like it's like giving us programs we could run now just on like a tensor network substrate. And we just didn't see it that way. So it's like really the amazing work happening in the 1990s was a family of classical algorithms, but we just thought you had to put them on special hardware, but maybe you don't. So that was kind of the feeling I came away with. That was a bit mind-bending for me, because I'd always just assumed when you see a quantum circuit, the very next thing you do is walk into a quantum computing lab and put it in the hardware. That's really what they're for, I thought. But maybe not always.
So how about Grover?
Yeah, look for the archive next week. That's what I'd say. Yeah.
Because Grover, Grover is like a even more extreme example of this, because you start with something that's completely unentangled, then you end with something that's completely unentangled, and somewhere in the middle you have to go through, you have to climb up a hill, right? And that's probably where the volume law or like something like some high entanglement structure will show up. But
the punchline is that, it's very similar to Shor's in that way. So there's sort of two parts. There's like the oracle, which is a lot like the first part of Shor's, roughly speaking, where there can be this very high entanglement barrier in general. So, otherwise like P would equal NP or something that we know probably isn't true. But then the other part, the kind of post-processing part, which is roughly like the QFT, its job is to extract the answer out. Well, Grover's, what plays the role there? It's just the kind of outer part, the loop of Grover's, where you just switch back and forth with this diffuser and do all those kind of things.
You mean in the phase estimation part for the latter part?
Not really phase estimation, but just this kind of overall framework of doing this sort of 2 to the n over 2 steps. That part can basically be dequantized. And this was actually already noticed in a PRL by Jielun and Mucciolo, where they just show that you can, by kind of thinking of an MPS in this same way, like representing a function, you can kind of do like a binary search algorithm on the function. Like basically, if you have a hidden delta function somewhere, you can just kind of integrate the left and integrate the right. And one of the integrals will be 0 and one of the integrals will be 1. Then you can just throw away the side that's 0 and then kind of zoom in, zoom in, and zoom in. So in very efficient classical algorithm, you can like pick that value out actually. So it sort of has the same feeling as like this QFT Shor's algorithm thing, where it's got 2 parts and one is very hard in general and one is like classically pretty easy actually.
Wow.
But you have to use an MPS. That's always the.
Yeah, in fact, you can do like even more, even easier. Say you get a SAT problem and you write your clauses as MPOs that you apply to an initial MPS. That is your the equal amplitude superposition, right, of all your configurations. And then you can see you can track the entanglement, and you see you have to go over a hill and then come back down. Also a paper by Jielun and Mucciolo. Yeah. The hope is always that you can tunnel through that barrier somehow to avoid clearly if you were to have a quantum computer, you can do this because you don't care about building up entanglement, but
Yeah, this I'm very interested in right now too, because there was 2 papers last year. I think maybe we were chatting about this the other week, but one paper by this group, like I think it's Joel Moore's group there at Berkeley, where they also looked at the QAOA algorithm, and they found that in many cases there's an entanglement barrier. So it shows you that you really would need a quantum computer to carry it out. But then I forget the authors, I should have looked this up, but there's another paper that came out around the same time last year, where they just sort of boldly tried to tunnel through that barrier by just capping the entanglement by brute force. And they found, I don't know how often, I'd have to go look, but they found that in many cases, if you just did this tunneling kind of by force, you could still sample out a very good solution at the end to the classical problem. So somehow it gives you the feeling that the entanglement barrier is very high, but maybe you don't need all that entanglement, you just need some of it to solve it.
That's right, yeah. Which part of the entanglement is useful, right? Because if you think about, say, DMRG for like some algorithm that looks for a ground state in MPS form, then quantum fluctuations are really important. So you don't just need the dominant classical configuration, you need all of the fluctuations to describe a state properly. But in these problems where we're looking at decision or optimization, we just care about one component or a few, right? So it means that a lot of the entanglement is actually not working for you, it's just there.
Like some byproduct of the details of how the algorithm was written down, you mean? Something like that?
Yeah.
I see that in the Q&A, there's a question that is actually very much related to this, that goes about a result of Maarten van der Nest that deals with universal quantum computation with very few entanglements. So as far as I remember, but I'm not sure that this is exactly the answer to this question, but it is clear that you can have states with very, very small, arbitrarily small entanglement entropy that you cannot approximate with matrix Prolog states. This is actually a paper that we wrote together with Ignacio Sirac and Norbert Schuch, that actually the von Neumann entropy doesn't really care about the small Schmidt coefficients, and that's why it's not really kind of good enough to reveal all the entanglements. So indeed, the small stuff is very important sometimes. And what you need to do then is typically use Renyi entropies with alpha smaller than 1. And these are actually, well, you know that the Renyi entropy of alpha goes to 0, then this is really the rank of your state. But between 0 and 1, they have like the properties that are interesting. And as far as I understand, the Renyi entropies of these states actually have lots of entanglement, but maybe somebody else has a better view of this, or can answer this question better.
That was a great answer.
I think it's a great answer. Yeah. I mean, I think in practice, when you try some of this stuff out, I mean, Stefanos has been trying these things out longer than I have. But one neat thing, of course, about NP problems is that you can check your answer at the end by sort of definition of that class. And you can just try, you might observe a small entanglement, but if you then naively think, well, it means I can truncate very heavily, you might just plug it into your NP check at the end and just get a totally terrible answer. So you might just find in practice you need a large bond dimension, which would tie back to what you said, Frank, that it's just telling you that the tails are important in that case.
Oh, great. So maybe, well, really nice to see you, Frank and Miles, and great to meet you, Stefanos. So this was a wonderful panel. You really brought this subject to life in a wonderful way. And thanks, Chris, for a great talk. That was super clear, really nice, very inspiring.
Well, thanks
everyone
for inviting us.
Congrats, Chris.
Thanks.
Okay, anyway, see you guys.
Yeah, great. See you guys.
See you another time.
Right.